For the first time in human history, we have the ability to decode marine mammal language. Because some of the sounds are behind our hearing range, and in the past we didn't have the proper gear and techniques to properly record sound underwater. The objective of the project SETI, that SETI with a C, is to understand sperm whales. And the lifelong work of Denise Herzing has been to understand dolphins, and she's been studying the same dolphins in the waters of the Bahamas for the past 30 years. And so when you look up information about this, in these videos they're describing techniques. They either hit you with the blanket term algorithms, or they throw around a bunch of technical terms to overawe you with their science, but not really explain what's going on. What I want to explain today is the progress of the work done and make it easy to understand the programs behind this work so that you're empowered to use the open resources available to get involved yourself. So one such technique is researchers are using 3 hydrophones, a specialized underwater microphone, to triangulate the sound, find the source, and add metadata to the speaker. They've also, in the case of Project SETI and sperm whales, is they put a suction cup with the microphone onto the sperm whale so they can see everything it's saying as it goes around. And what they've been able to figure out so far, at least in the case of dolphins, is that dolphins have names. They concluded that the signature whistle is how dolphins identify each other, and they found this out after seeing the whole group of dolphins making a frequency modulated whistle that had one dolphin change course to return to them. And the dolphin in question was making the same frequency modulated whistle while it was swimming around having fun. It was making the sound over and over again. Dolphins develop their own signature whistle while they are calves in resemblance but distinct from their mothers. So I just use that term frequency modulated whistle. What is that?
Dolphins make basically 3 types of sounds. They make frequency modulated whistles, echolocation or sonar clicks, primarily used for navigation and hunting. First pulse sounds. And these are social sounds that you would hear during fighting, mating, that sort of.
Sperm whales have many patterns of clicks that make up their complex language. The most common are clicks used for long-range echolocation, like sonar. And then there's close-range creaks for when prey capture is imminent. And finally, codas are distinct patterns of clicks most often heard when whales are socializing. And these vocalizations are of particular interest to scientists. Sperm whale codas sort of sound like Morse code, and the patterns of the clicks are distinct among social groups, with each clan having its own specific repertoire of codas. These codas are the social glue that holds the clans together. Females use codas more than males, which makes sense when you think about how they raise their young.
Are there methods for learning a language completely from scratch? There's actually a world premiere expert on this, the author of Don't Sleep, There Are Snakes, Daniel Everett. He claims that language started not with Homo sapiens, but with Homo erectus. In this talk he gave in San Francisco, he talks about a language with only 10 distinct sounds as a fully functioning language. So let's use his words for defining a language to distinguish it from mere communication.
A language is just, in essence, 2 things: symbols and grammar. And how many symbols do you need and how much grammar do you need? What's a symbol, first of all? The symbol is conventionally a sign that is conventionally or culturally connected to its meaning. So take the number 4, F-O-U-R, or hold up my fingers, 4. That means what? It means a cardinality of 4. We have to keep talking in English. But 4 is a culturally determined form and a culturally determined meaning. Not all languages have mathematics. Peter Ha, for example, doesn't have even the number 1. There is no mathematical concepts in that language whatsoever. So math is a cultural discovery, if not a cultural construct. And I have identified 3 kinds of grammar in my field research over the last 40 years. One I'll call G1, and the next one is G2, and the last one very originally is G3. And G1 grammars are just grammars in linear order. And we have examples of this in English. You drink, you drive, you go to jail. No shirt, no shoes, no service. It's just words in order. But the next kind of grammar, a G2 grammar, and let me point out that there are modern languages such as Riau of Indonesia and Pidahan, in which Serious psycholinguists have argued that their grammars are of this G1 type, just words in linear order. A G2 grammar has hierarchy. So if you drink and you drive, then you go to jail. You take the words and you make a larger sentence. And a G3 grammar has hierarchy and recursion. If you drink and you drive, and you know you shouldn't do that because your wife's going to get really upset because her father told you the last time that you did that he was never going to give you bond money again, and so you can just keep on going. Those kinds of grammars are found commonly in the world's languages, but you can express anything from a G3 grammar in a G1 grammar. Mathematically, they're all of equal power. So once you have symbols in a G1 grammar, you have language, full-blown human language. We find.
Are whales and dolphins smart enough to make this jump into grammar?
This feature, this behavior that makes humpback whale song so unique in the whole animal kingdom. So an entire population, which can contain over 10,000 males, will rapidly and synchronously change their entire song display, which can be up to 30 minutes in length for one song. They will change this to a new song, which has been introduced from a neighboring population. It's like changing your national anthem every 2 to 3 years to something that your neighbor has been singing. And this makes absolutely no sense at all. Birds really don't do this. In fact, the only other animal that makes these kinds of population-wide changes at this vast and rapid pace are humans. Hopefully, we're just going to listen to one phrase. Now, this is a spectrogram, so frequency, so the pitch is in kilohertz on the y-axis and time in seconds on the x-axis. Now, each part is the sound, and for this example, we have a bellows and 3 croaks, and if I'm very lucky, it will play for you.
Has there ever been an attempt to speak dolphin language?
So the way it works is we're in the water. I can push a sound, for example, this is the whistle for scarf. This headset just said scarf in English, so I know that's the sound I played. Now, if the dolphins decide to mimic this whistle, they'll mimic it. The computer will recognize it in pretty close to real time, and I'll hear the word scarf in my headset. Dolphins, when they greet each other, use their signature whistle, so we thought it'd be pretty cool to give ourselves a name. So that's my name, Denise. Now we also have some of their signature whistles in the computer. That's Brat. He's a little brat, and he's one of the players in the system. So we can greet him in his own name. So we thought that would be a start to trying to communicate with the dolphins.
So there has been, but the video goes on to explain how the devices were made. It never tells you if the dolphins actually started using the word scarf. I thought that mission was a little grandiose because they were making up a word for scarf and they were making up a signature whistle. Have you ever spoken a different language and you practiced and practiced until you thought you had it right and the native speaker was still at a loss for what you were saying? Now you know how I felt whenever I walked into a hotel and said cocktail. I feel like without that dolphin group knowing Denise Herzing's mother and what her signature whistle was, they were just kind of like, huh? What's going on? That sounds like a dolphin, but it's not making any sense. With this synthesized dolphin voice blurting out a sound that was supposed to be Denise Herzing, they got a little overconfident with what they were doing. But how did they get confident enough from the data to think that they can make an attempt like this?
Just use machine learning to translate between 2 totally unknown human languages, not by using a Rosetta Stone or a dictionary, but by mapping them on patterns in higher dimensional. In the past half century, marine researchers have painstakingly collected and hand annotated just a few thousand sperm whale vocalizations. But in order to learn sperm whale communication, we'll need to collect millions, if not tens of millions, of.
So what he's talking about is word vectors, where the meaning of words are translated to numbers. And he's committed what's a sin to me in talking like the use of this concept is the end-all be-all of translation. And translation has captured every nuance, sense, and avoided every misunderstanding. To give you an oversimplified example of what it means to map word vectors, red could be 2, then a shade maroon could be 1, and that a hue scarlet would be 3. But it's not always that simple. Sometimes even the word with the right feeling will not capture metaphors and turns of phrases will go unheard. This is a notorious failing of Google Translate, and if you don't believe me, go to Georgia and try to use Google Translate to talk to people. And so, whenever I was making my own translator between English and Russian, I tried to use word vectors to categorize English words by their synonyms and hoped Russian would follow a similar spread. I was using the word vectors provided by the special natural language processing library called spacy. That's SPACY. And I didn't figure out what was going wrong until I read this book, The Russian Wordsworth. So what quirks could the dolphin and whale languages have that we're not accounting for? Gendering words first appeared in human language in the Proto-Indo-European languages and has been a trait confined to its descendants. What I'm hoping for is some conclusion on the total amount of sounds dolphins or whales can make so that we can try to hypothesize an alphabet. So we can see what combinations of these sounds are reoccurring and in what context.
So easy. So here's A-L-E. So that's a pattern that the computer can now label. So now when I look at that stream of sound, I can see, oh, A-L-E. There's another A-L-E. Now we're getting into, is there order and structure to their sounds? Which language you would think would have some kind of order and patterns? Do certain sounds always cluster together? Does that mean they mean something? So that's really the power of what this program does. The time it takes for a human to do that is ridiculous. So you can mine your data differently and get these patterns, and then you can start looking at it from a biological point of view. Does the ALE cluster always show up when a mother and calf are together, or certain mother and calf, or when they're fighting, or whatever? And the other big point is that, do they recombine? So like we've always measured a whistle as a unit of information, but is that true for dolphins? Maybe they have an upsweep and a downsweep and another flat kind of whistle, and maybe they recombine them to mean different things. That's what human words are, basically. That's how you get the power of language, is you recombine segments of sound and you get different clusters. So we don't know if dolphins do that. No one's ever looked at it before. No one's ever had a computer tool to do that, really.
So what tool is she talking about and how is she analyzing her data? The techniques they're using on the data they're recorded to extract meaning is machine learning and deep learning. One example of deep learning is neural networks, and this next clip will show you how neural networks are being applied to this project of deciphering.
By matching thousands of orca calls on the input side with a target value on the output side, they train neural networks. These layers of neural networks then learn bit by bit which sounds are typical for orcas.
What makes neural networks special is they can classify data that doesn't cluster based on traits. So feeding data into a properly trained neural network can give you insights you weren't expecting. One complication of this is neural networks have to have an answer weighting. There has to be an X and a Y. The output it should generate needs to be known is because neural networks are just for finding the best way from point A to point B. They automatically use a technique called backpropagation to correct what veered off course and didn't match the end result. And unsupervised learning such as clustering can provide a means for finding an answer because it will find possible groups based on data. Having input with multiple features means these algorithms have to go into higher dimensions to account for all possible combinations. This is a good thing because of the inherent complexity of our problem, because it will form more meaningful groupings at the trade-off of requiring a lot more data. Some examples that could be very useful on the data at hand are hierarchical clustering or DB scan. Say we're trying to figure out the parts of speech of the dolphin language. And human language is never this simple, but let's make a hypothesis that every frequency modulated whistle is a noun. We can make a data frame in the Python's pandas library, subset samples where frequency modulated whistles are heard, make a column for how many times the sound is heard in the sample, associate an ID number or numbers with the specific vocalizations heard in the sample, a column for the metadata, run it through our clustering and see if ID numbers end up in the same group similar metadata. This paper says that using unsupervised learning techniques such as clustering to get possible labels and then seeing if neural networks will reach the same conclusion given an unseen data set. This is an intuitive part of the process of artificial learning, where data sets are split randomly into training and testing sets. You know you can do this too. This paper describes an audio processing library which can be used with Python called Triton. It's available on GitHub. It can run on 32 gigabytes of RAM with a 4-core CPU. My 7-year-old laptop has that. So when you're doing this, you want to look into densities, abundances, patterns, and match over locations or times. So I've equipped you with everything I know. If you want to know more about programming, I recommend Python, and I got Python tutorials. Perchance you want to learn Russian, I got the hottest app on the Google Play Store. It's called Kangaroo. I also wrote a story about what if the oceans dried up, and it's called The Water Maker. And it should be done soon. So this is goodbye until the next Data Science for Everybody.